Okay, so until now we've been speaking exclusively about classification. And today we will move on from classification and talk a bit about, so far we've been speaking exclusively about regression, in which the target variable is continuous. And today we'll move on from that and we'll start to talk about classification, where the target variable is not continuous, but takes on one of a set of potential values. So let's start by talking about the premise of this problem. We have a set of data points. So we have a bunch of feature vector label pairs. Each X is a feature vector, each Y is a label. And we know there's some relationship between X and Y. And we'll talk about kind of two varieties of classification. In general classification, the output variable Y is constrained to be some integer value from 1 to K. K is a number of classes. So for example, suppose I have a photograph of an animal and I want to classify it as being, let's say, cat, dog, elephant, sheep, lion, etc. So K will be the total number of animals I know about to classify. And each value will be associated with an integer. And I'm going to try and produce that output variable Y as a correct integer. The alternative is binary classification, where the output variable is constrained to 0, 1. So imagine I have a photograph classifier that takes photographs and says it is a cat or it's not a cat. Okay. So if the photograph is of a cat, I'm going to output 1. If the photograph is not a cat, I'm going to output 2. So this is the premise of a problem of a classification problem. Now we'll start by talking about linear classifiers. So let's make a little drawing here. What is a linear classifier? Okay, so suppose I have some data. My data has two features, x1 and x2. And I have, let's say, two possible values for, stop sharing. Okay, I have two possible values for y, 0 or 1. And I'm going to represent the two possible values for y using colors. So a 0 will be an orange value. Okay, and let's say these are my zeros, and a 1 will be this purple. Okay. So what would a function that classifies these two look like? So I'm looking to, let's say, for a given x1, x2 pair, so let's say this point right here has this value on the x1 axis, this value on the x2 axis, and I want to be able to classify it as, let's say, a 1. So you can see from looking at it that you could potentially just draw a line. Let's draw a line like this. Okay. And this line separates the two classes. We're going to call this line a decision boundary. Okay. And it separates the 0 class and the 1 class. Okay. This line has some equation. Right? So the line is, let's say, W1 x1 plus W2 x2 equals 0. Just like all the other lines we've been discussing. So we can write an equation of a line, and then we can say, okay, for any new point, we'll plug the new x1 and x2 into the equation of the line. Okay. And I'm drawing an arrow here that points to, let's say, the positive side. So let's say this is the equation of the line. If the value here is greater than 0, so the line is set equal to 0. If I plug in a value for x1 and x2 with these weights, and the value is greater than 0, that means it's above the line. So on this side of the line, all of my values are 1. So my class values are 1. If I plug in an x1 and x2 here, for example, then it's going to come out less than 0. It's below the line. And that means that the coefficient, the target variable is 0. Okay. So we can see here, we can draw a linear decision boundary that separates the two classes, a 0 and the 1 class. And if the new point is in this, what we call decision region, corresponding to class 1, then we say that y hat is 0. If it's in the decision region corresponding to class 0, then we say y hat is 0. Okay. So summing that up, we could say we have some weight vector, and we can compute this linear combination. So just describes this line where z is equal to this line, the equation of the line. And then we could predict the class based on whether it's greater than or equal to 0. Okay. What about if I have multiple classes? How can I extend this to multiple classes? So let's say I have a 2 class also. So if I have a 2 class, well, I can still add another line. So I can have basically a line separating each class. So then I would have, instead of just having one linear equation, I would have a set of linear equations. And I can compute the value for each to find out where my new point falls. Now, in this example, I'm going to remove the extra class because we're going to go back to the binary problem. In this example, we can say that this data is what's known as linearly separable. I'm going to write that down. Okay. The data is linearly separable if there is a hyperplane such that all x's in one class lie on the positive side and all x's in the other class lie on its negative side. And this generalizes to the multi-class situation as well. So here's a multi-class situation. This is a much better picture than the one I drew. So you have a set of hyperplanes that separate the examples of class I from the examples of all other classes. And we say that the data is linearly separable if there is a hyperplane such that all examples of class I lie on the positive side of hyperplane I, and all negative examples of class I, meaning they're not class I, lie on the negative side. What would be an example of a data that's not linearly separable? So let's say I took this point and I put it here. Is the data now not linearly separable? Well, actually, I can just take this line and move it a little, rotate it a little. And there still exists a line that separates the two classes. So the data is still linearly separable as long as there exists a hyperplane that can separate the two classes. Now, take a look at this hyperplane. Is there only one hyperplane that separates the two classes? Okay. So I have, let's say, this potential line that separates the two classes. But I also have this potential line, right, or this potential line. And you can think of it as kind of like adding some epsilon to any of the coefficient values of the line. Actually, if there's a line that separates the two classes, there are infinitely many such lines. So this is what's known as the non-uniqueness of the separating hyperplane. If there exists a hyperplane that separates the classes, then there exists infinitely many such hyperplanes. That's one important property. Second property is, well, not all data is linearly separable. So in this example, my data is linearly separable. But if I would put some point here, for example, then we know that it's not linearly separable at all. So there is no hyperplane that can completely separate the classes such that all examples of the positive class lie on the positive side, all examples of the negative class lie on the negative side. for this example, no matter where I put this hyperplane, I cannot satisfy that property. So this is an example of data that's not linearly separable. Okay. So with that in mind, well, we have the challenge of trying to find the hyperplane to separate these points, right? So we're looking for a line. These parameter values W will define where that line is, so where the hyperplane is. And we have the challenge of trying to decide the coefficient values. What coefficient values should we choose? So first of all, we know that if the data is separable, there are infinitely many coefficient values that can separate the data completely. And let's think for a moment about how we might evaluate this. So we can think, for example, about a 0-1 loss function, where you, let's say, add up the number of points classified correctly and divide them by the total number of points. Okay. So in this example, 100% of points are classified correctly. So the 0-1 loss function is, perfect. The 0-1 accuracy is perfect accuracy. But that's also the case for all of these other kind of hyperplanes I'm producing as I move or rotate this line. So which hyperplane should we pick? Is this the best hyperplane to pick? Or let's say this one. Maybe this one is better. Or maybe this one is better. So the first question is which hyperplane to pick. Evan says we pick the hyperplane that maximizes margin. Not necessarily. That's one way to do it, but it's not necessarily the way we're going to do it today. And then we also have the challenge of what if the data is not linearly separable? How do we pick the hyperplane then? So today we're going to talk about linear logistic regression, which is one way of finding a hyperplane that minimizes loss according to some loss function. Okay. And we know that in general in machine learning, we're always tuning parameters to minimize some loss function. So logistic regression defines one loss function that we can try to minimize. Later in the semester, we'll define other types of classification with other loss functions for the same problem that might arrive at slightly different separating hyperplanes. Okay, so logistic regression is one example, but we'll look at others throughout the semester. So let's think about logistic regression. Now, one way you might think about doing this is, let's say, fitting a linear regression model to your labeled data. Okay. So let's actually start a new one here. Okay, so let's imagine we have data on a line. So we have just one feature, x1. Okay, and let's say this is a 0 point. So we have, let's say, some 0 samples here. And some 1 samples here. And the 0 point is here. Okay. So we talked about having a line that separates these, right? So we know that there are many possible lines that separate these, right? This is one line. This is another potential line. These are all potentially separating lines. There's actually only one feature. So these are all potentially separating lines. Okay. Now, one way to, let's say, solve this problem could be to train a linear regression on x1. So what if you train a linear regression on x1 and you say that, okay, if the output of the linear regression is above 0, then I belong to the purple class. If the output is below 0, then I belong to the 0 class. Would that work? So basically, a positive output for the linear regression means belonging to the purple class. A negative output means belonging to the 0 class. Do you think that would work? Well, conceptually, it's a little bit awkward, right? So you could imagine that, let's say at this point here, the linear regression might produce some value like 2671. Okay. And then we're, let's say, rounding it to the nearest value. So let's say we'll round that to 1. I don't know, it's very like conceptually messy to think about rounding 2671 to 1. And if we round, let's say, -345 to 0, it just doesn't make a lot of sense to think about predicting y hat as some value of a linear regression. We know that the true value of y hat is always 0 or 1. And if we use a linear regression here where we try to predict y hat using some linear function, then we end up with values that are not really close to 0 or 1. It doesn't make a lot of sense conceptually, and it doesn't seem to make sense in terms of the loss function. And we know that our squared error loss function considers 2671 to be very far away from 1. And we want to have a loss function where, let's say, the output of the model is close to the true value. So conceptually, fitting a linear regression for classification does not really make a lot of sense. And more generally, it doesn't really make a lot of sense to try and fit a model that produces, let's say, y directly in this case, in this, let's say, linear case. So instead of looking for a model so that the output of the model is going to be approximately the value of y, instead, we're going to look for a model where the output of the model tells us the probability of the sample belonging to the 1 class or the 0 class. So we're going to look for a function that takes as its input x, and it's going to produce, let's say, f of x is equal to the probability that x belongs to the 1 class, the positive class. Or alternatively, you could say that 1 minus f of x is a probability that x belongs to the 0 class. So instead of predicting y directly, we're going to predict the probability that y is equal to 1. Now, since our prediction is going to be a probability, what do we know about probabilities? We know that they have to range from 0 to 1. So our f of x needs to be some function that will take some real value and map it to the range 0 to 1. What function should we use? So this plain linear regression is not at all mapped to 0 or 1. What could be a function that maps to any real value to 0 or 1? Okay, so we have many choices, really. I'm going to put a 1 here. So we're essentially looking for something where, okay. We're essentially looking for something where, let's say, for a range of input values, any values, it will be like this, and eventually it will go to 1 and stay there. Okay. So a few options are possible. So you could have a hypertangent, you could have a sigmoid. We're going to use a sigmoid here. A sigmoid looks like this. So it's a classic S-shaped function. It's defined as, let's say, sigmoid of z is 1 over 1 plus e to the minus z. And the reason we like the logistic function here is it actually has a nice derivative, which makes an easy update rule if we want to train it using gradient descent. And as a probability, it also has a nice intuition. Right? So remember over here, so we said that, let's say we have some equation of a line. So we have, let's say, some equation of a line like that's shown here. And now instead of trying to predict, let's say, whether a particular point is above or below the line, we're going to try to predict the probability that a point is above or below the line. Okay. Now, for a given point, we're going to compute For a given point, let's say this point, we're going to compute this value here. Now, for this particular point, this value will be, let's say, relatively large, right? And that's because this point is relatively distant from the separating hyperplane. When this value is large, the value of the sigmoid is close to 1. So if we take as, let's say, as z, this equation of the line, so we're going to compute this as z, put it into a sigmoid, and use that sigmoid to predict the probability of being equal to the probability of the class being 1. We could see that when a point is very far from the separating hyperplane, the z value that we use as input to the sigmoid is large, and so the probability is close to 1. Intuitively, this makes a lot of sense that a point that is very far from the separating hyperplane has a high probability of belonging to the positive class. This is in contrast to, let's say, this point here, which is much closer to the separating hyperplane. So the distance to the separating hyperplane is smaller. This value will still be positive, but it will be a smaller positive value. So instead of, let's say, ending up all the way over here because it's a large positive value, we might end up, let's say, here. Right? So here we would say that the probability of this point belonging to the positive class is still greater than 50%, but we're not as confident about the points close to the hyperplane as we are for the points far from the hyperplane. What other positive characteristics does this have? Well, one other thing is, let's say, what happens as the weights get larger and larger. As the weights get larger, so as the input to the sigmoid gets bigger, the slope of this part of the logistic function gets steeper and steeper. What does that mean? Well, in practice, it means that if we have points that are kind of separable, then we can use large weights. So remember, this is all equal to 0. So there's kind of a bunch of, okay, so we can use potentially very large weights. And then the sigmoid can be very steep. But if we have data that's, let's say, not linearly separable or kind of more mixed up, then we can have a less steep sigmoid function. And we end up with lower weights and a less steep rule. So the sigmoid function has these kind of nice intuitions behind it, in that it outputs a more confident probability if the value of a point is farther from the hyperplane. So this is kind of a nice feature. Okay, so now that we have chosen our function, let's talk about logistic regression for binary classification. So we're letting z equals to the dot product of wx. So again, this is just that equation of the line. And then we can say that the probability of y being equal to 1, given some point x, is equal to 1 over 1 plus e to the minus c. That's a sigmoid function for z. And the probability of y being equal to 0 is 1 minus this. So that ends up being e to the minus c over 1 plus e to the minus c. And notice that these sum up to 1. Now, once we output this probability, so the output of our model is not going to be a 0 over 1. It's going to be a value from 0 to 1 that represents the probability of belonging to the positive class. Now we need to turn it into a hard 0 or 1 label. So to turn it into a hard 0 or 1 label, we're going to choose some threshold such that if the probability of belonging to the positive class is greater than that threshold, we'll say the label is 1. If the probability of belonging to the negative class, if the probability of belonging to the positive class is less than the threshold, then we'll say that the class label is 0. So let's look at some examples here. So let's see. Okay. So you might adjust this threshold so that your kind of decision boundary, which separates a 0 and 1 class, classifies or misclassifies different points differently. What do I mean by that? Okay, so let's say this point represents the 50% threshold. So for a point that's on this line, there's a 50% chance of belonging to the positive class and a 50% chance of belonging to the negative class. Now, when you output these probabilities, you can make, let's say, a contour plot of probabilities. So this was the 50% line. Okay. And this might be a less confident one. A more confident one. So I'm not going to add up points here. But let's say we say that if a point is above this line, it has a 1 in 1, 2, 3, 4, 5, 6, 7, a 1 in 7 chance of belonging to the negative class, which means about a 0.85 chance of belonging to the positive class. And then you might have a similar situation here. So this might be a 0 threshold, where if a point is below this line, there is a lower chance of belonging to the positive class. Sorry, if a point is above this line, you might have, let's say, a lower confidence that it belongs to the positive class. So you produce, let's say, different thresholds for different confidence levels. And the one you select depends on your particular application. And I posted some notes online that I wanted you to read to think about this a little more. So these notes here. But the general idea is that it depends on the cost of different types of errors. So imagine that this classifier is a screening test for some dangerous disease. Okay. A screening test is not diagnostic. So if someone, let's say, tests positive on the classifier, then they undergo further diagnostics. Now, you don't want everybody to undergo the further diagnostics because it's expensive. On the other hand, the diagnostic is not that expensive and the disease is very dangerous. So you don't want to miss any potential patients with the disease. So in that case, you might choose, let's say, this particular classifier as the best classifier. This particular classifier, if you say, okay, everybody above this line is considered positive by the classifier and will undergo the diagnostic, there are some points here, like this point, this point, this point, this point, that actually don't have the disease, and they will undergo the diagnostic unnecessarily. But that's okay because the cost of that type of error is pretty small, right? We said the diagnostic it's inexpensive, it's non-invasive, it's not such a big deal. On the other hand, if you chose this line over here, well, the benefit of this line is you're not catching many people who don't have the disease. So only one person will unnecessarily undergo the diagnostics follow-up. On the other hand, you're missing many people who do have the disease. So all of these purple points below this line are not going to get flagged for the diagnostic. So in this case, the cost of, let's say, misclassifying a positive example as negative is much higher than the cost of misclassifying a negative example as positive. So you would probably pick this line, so the threshold here. On the other hand, if you had, let's say, a different problem, so let's say now your classifier is a screener that looks at blood samples from pregnant women and predicts whether the fetus is a male or female. So the cost of misclassifying a male or as female fetus and vice versa is pretty similar. There is not a higher cost to one type of error. So in that case, you would just pick the threshold which maximizes accuracy, which is just the 50% threshold. So this threshold lets us kind of tune the classifier to favor one type of error or the other. Okay, so the properties of our logistic classifier. The class probabilities depend on how far you are from the separating hyperplane. A point that's very far from the separating hyperplane will have a probability of approximately 0 or 1. And we said that when the norm of the weights is large, the sigmoid becomes steep. So the class probabilities go towards the extreme more quickly. Now, the logistic classifier had a lot in common with the linear regression, but some things are different about it. So unlike the linear regression, the weights don't tell us what a 1 unit change in input will do to the output. So that kind of interpretability is no longer there. However, the sign of the weight does tell us about the relationship between the feature and the variable. So if a particular feature has a positive weight for the logistic regression, that tells us it's more likely to belong to the positive class if that value is larger. Okay. Now, how do we extend this to multiple classes? So far, we're only talking about binary classification. Now, suppose we have multiple classes, classes up to k. So instead of having a weight vector, we're now going to have a weight matrix. And I'm always going to assume that that ones column is stacked at the beginning. So you have an intercept rolled into the parameter matrix. So we have a weight matrix that's k by d, where k is the number of classes and d is the number of parameters. And that means that when we compute for a given x, when we compute, let's say, wx, so we multiply these, then we end up with z, which is going to be a set of k linear functions. So you could think of the weights as a set of weights for k linear equations. And when we compute z, we'll end up with k values for z from the k linear equations. Now, for the logistic regression for binary classification, we use the sigmoid function. And the output of the sigmoid told us the probability of belonging to the positive class. For the multi-class version, we're going to use a softmax function, which is very similar. The softmax function takes as input this vector z, which has k numbers in it. And it's going to output k different probabilities. Okay. So g sub 1, for example, is going to be e to the z1. So remember, we have the z, let's draw it. We have, let's say, z1 all the way up to zk. So that will produce, let's say, a bunch of g's, g sub 1, all the way up to gk. So g sub k is going to be equal to e to the z1 divided by the sum of all the e to the z's. So I'm going to compute the sum e to the z for each of these z's. And then each of my entries in my G matrix, my G vector, is going to be equal to, let's say, e to the z1 over that sum, then e to the z2 over that sum, and so on, all the way up to e to the zk over the sum. So it takes as input a vector of k numbers, and it outputs k different probabilities. And each probability, each G sub k, is going to be proportional to the exponential of that z, so that input. And that tells us the probability of belonging to class k. Okay. So if, for example, g sub 1 ends up being close to 1, and all the other g's are close to 0, that tells us that there's a high probability of belonging to class 1 and a low probability of belonging to any of the other classes. Okay, so the softmax function kind of acts like a probability mass function. It has some nice properties. It's in the range 0 to 1 for every individual k. And also the sum of g sub k for all k values will be equal to 1. And it also has a property that a large input, so if z sub k is large for a particular k, then g sub k will be larger. So if you remember when we talked about, let's say, multi-class classification, we talked about having multiple separating hyperplanes, one for each class. So that's exactly what we're doing here. We have k linear functions, each defined by a separating hyperplane like this. And then we compute the value of this function, which tells us how far above the separating hyperplane for the kth class we are. And it produces, as a result, some probability of belonging to the kth class. So we have our class probabilities are given by that g sub k function. And then we end up with k of these, where k is a number of classes. So this is a probability of belonging to class small k. And in general, if we have one z that's, let's say, much larger than the others, so this is for multi-class classification, but we'll look at it in the binary example because that's easier for me to draw. Okay. So if you have, let's say, let me draw a different one. Okay, so let's say we have another class here. So if you find that, for example, your point is over here, right, you'll have a very large value for this line and a much smaller value for this line. So then you'll find that your g sub k for the green class is close to 1. Your g sub k for the purple and orange classes are close to 0. And in general, you assign the highest probability to class k when the z sub k for that class is largest. So then it's easy to, let's say, set the class value just according to which g sub k have the largest probability. Or in other words, you get a vector of probabilities, one for each class, and you can say, okay, the class label is going to be the most probable class. Okay, so we've described the logistic regression for both the binary case and the multi-class classification case. We know that in each case, we're going to basically find the weight vector for this separating hyperplane. And once we have the weight vector for our separating hyperplane, then we can, let's say for a new point, we can compute the value for that for each separating hyperplane, one per class, feed it into either the sigmoid or the softmax function, and then assign a class label for which the logistic regression predicts the highest probability. So we know kind of a lot of steps for our machine learning recipe. We know how we're going to do inference. We know what our parameters are going to be like. We know what the model class looks like. Now we need to know how to actually train the model. What do we need in order to train the model? Okay, so we had a machine learning recipe. For our logistic regression, we have data. We have a candidate model, so we have an f of x, which is kind of either equal to sigmoid or the softmax. We have a way to predict y for new samples, so we know how to do inference once we have the weights. But we still need a loss function, so we need to be able to evaluate how good a prediction is. And we also need a training algorithm to find the weights that minimize the loss function. So that's what we're still missing. So let's talk about how we do that. So our weights are the unknown model parameters. We have k by d matrix of weights. So k is the number of classes, d is the number of features. And we know that the probability of belonging to a particular class is going to be equal to g sub k of the weight matrix times x, where g sub k is that softmax function. And then we have a set of training data that will allow us to learn w, that weight matrix. Now, what loss function should we use to find the optimal weight? The relationship between, let's say, the accuracy of the model and the weight vector is not completely clear. to find the optimal weights, we're going to find the weights that are optimal according to what's called maximum likelihood. So this expression here tells us the likelihood of belonging to a particular class for a particular sample. Right? This says, what is the likelihood that Y belongs to class K? Now, let's think about a vector of Ys. So we have a bunch of training examples. Each of them has a Y value. So we have a vector of Ys from all the training values. And we also have a matrix of X's, so a feature vector for each training value. The maximum likelihood estimate of W, the weights, is the set of weights for which the probability of Y belonging to whatever class it does is maximized. What does it mean? Well, let's say we have this example here. We will want to find the weights of the line such that, let's say, if we add up for all of these points, well, okay, not actually add up, let's say multiply for all of the points because they're all independent, so the probability is multiplied. Okay, well, let's think about it this way. Suppose my separating hyperplane, I'll go back to the 2-class example. Suppose I had some, let's say, weights over here. Is it very likely that if this was, let's say, the true function, I would observe these particular Y values? So the data is kind of noisy, right? There's some noise in the data, but let's actually put the line here. Okay, so imagine we have some noisy data and there's some true function, let's say a true line that separates the 0 and the 1 class, not necessarily perfectly because the data is noisy, but there's some true function. Now, if this was a true function, is it very likely that I would observe these particular samples? So it's not, right? Because for the true function, I expect it to kind of separate the class as well. So I would expect to see kind of more orange points on this side and maybe fewer of the orange points on the positive side of the line. So if this was a separating hyperplane, it's not very likely that I would observe these class labels. What about if the separating hyperplane is 0? Is it likely that I would observe these particular class labels for this, if this was a true function? So that's not very likely either. What we're looking for is the separating hyperplane such that our observations make sense. So we're looking for the weights that maximize the probability that we would observe these particular Y values for the training sample. So this is what's known as the maximum likelihood estimate. Now we said that our outputs are each independent of each other. So each of the training samples are independent of one another. So if we're looking for this probability of, let's say, this entire vector X, this entire vector Y being observed, that's equivalent to multiplying the probabilities of the individual Ys being observed because the Ys are independent of one another. So with our outputs Y being independent, we could say that the probability of observing this vector of Ys given X and some W is equal to the product of probabilities of the individual points being observed. Now, products are not so friendly to work with. We prefer to work with sums. How do we turn this into a sum? So to turn it into a sum, we're going to take the log of both sides. The log has this property that the log of products is equal to the sum of the logs. So we're going to take the log of both sides, and we're also going to make both sides negative. And this is what's known as the negative log likelihood. So we're going to define the negative log likelihood, L of W, as minus log of the probability of observing a vector Y given X and some W is equal to minus the sum of the logs of the individual probabilities of observing individual points. And this expression here is called the cross entropy, by the way. Now, notice that maximizing the likelihood, so we said we wanted to maximize this. Now we took the log of both sides and set it to 0. And we took the log of both sides and made it negative. So now maximizing this is equivalent to minimizing this expression. So now we have a loss function to minimize. We want to minimize this negative log likelihood function. That will give us the weights such that we have the highest probability of observing the actual values that we observed. Okay. So we can rewrite our loss function as, instead of maximizing the probability, we can minimize the negative log likelihood. Now, for binary classification, I'm not going to go through this algebra slate, so you can read it later. For binary classification, we end up with the following. So we're going to plug in the sigmoid into this probability. So you can see we took this sigmoid. We're, let's say, making a sum of probability of belonging to class 1 versus class 0. Okay. So if, okay, do that. Okay. So notice that this expression is going to be 0 if the point belongs to class 0. This expression will be 1 if the point belongs to class 0. And so this sum tells us the probability of belonging to either class. And then we plug in that sigmoid, and we can arrive at the following expression. So this is the value of the negative log likelihood loss function for the binary classification. So this is a quantity we want to minimize. Now, it turns out that this is relatively easy to minimize using gradient descent because it has a very nice, friendly derivative. So it's easy to minimize, and all we need to do is use some numerical optimization procedure like gradient descent, and we can find the weights that minimize this value. For the multi-class classification, the expression, well, the procedure is the same. We're going to plug in the sigmoid to that loss function, into this function. But it's going to look slightly different. So now suppose we have a vector which says for a sample from class K, only the kth entry is 1. So this is basically an indicator vector. And then if you, let's say, do all that algebra, the cross entropy loss function comes out to this. So this is a quantity we want to minimize in the multi-class case. This is a quantity we want to minimize in the binary case. Now, to minimize, we would take the partial derivative, but it turns out there's no closed form expression here. But we can still estimate weights pretty easily using numerical optimization, for example, gradient descent. Now, we're going to stop here. I think a lot of this will make kind of much more intuitive sense on Thursday after we look at the collab lecture. But at least for today, we kind of completed our recipe for logistic regression. So we know that we're going to, as our model, we're going to compute the probability of y belonging to some class K given features x using either a sigmoid or a softmax function. We're going to use a set of labeled examples to fit the data to minimize a cross entropy loss. And we can use some numerical optimization procedure like gradient descent to find those weights. And finally, we can then use our model to predict y hat for some new unlabeled samples. Now, this is all I have to say about logistic regression. But in Brightspace, I shared a bunch of notes with you that are not specific to logistic regression, but are about evaluating the performance of a classifier in general. So we talked about this cross entropy loss function. This is used to train a classifier, but it intuitively doesn't really tell us a lot in terms of the performance of a classifier. So even when we use a cross entropy loss to train the classifier, we'll still typically use other metrics to evaluate its performance. So I'm going to ask you, if you have a couple of moments before our lesson on Thursday, to read through this set of notes, which describes various ways of evaluating the classifier performance, and then answer some questions at the end. Okay. Questions. Ben asks, assuming labeled data, will this loss function attempt to maximize the correctly classified data for each class? That's a good question. The answer is that to some extent, it depends what you mean by maximize correctly classified data for each class. It also depends on, for example, where you put your threshold. We'll talk about that a little more on Thursday then. Are there other questions? Okay,